Good afternoon, everybody, and welcome to the next OpenUK Future Leaders training. Just a little introduction about OpenUK Future Leaders Group. We are a collection of individuals who are interested in open technology, including open source software, open hardware, and open data. It includes a wide range of people that work in technology, intellectual property, outsourcing, procurement, data, coding, and innovation, as well as private practice lawyers and in-house counsel that work in the technology sector and related fields. It operates under the direction of OpenUK's Legal and Policy Committee and has a clear purpose to bring together and develop future leaders in legal and policy matters relating to open technology and support and further the mission of the Legal and Policy Committee. The Future Leaders Group is currently co-chaired by me, Robert Grinnells. I'm from Phil Fisher, and I'm an associate technology lawyer, and Katie Gibson from Bristows. She's also a technology lawyer, and we both advise on technology and commercial matters. The group is always open to new ideas and new members, whether you'd like to get involved in all of our activities or just dip in and out of our various projects. And I'm delighted today to say that we are welcomed by two fantastic speakers, Andrew Katz and Steve Helvie. Andrew Katz is the managing partner and head of technology law at Moorcrofts and CEO of Orcro Limited, and is the pro bono general counsel for OpenUK. And Steve is the VP of channel development at the Open Compute project. And I think it's quite apt that naturally our topic today is open hardware. And I think now's a good time for me to hand over to our speakers, Andrew and Steve. Thank you very much. And yeah, welcome.
Excellent, Rob. Thank you very much indeed for that. So during the course of this talk, I think it's going to be a little bit more free-form than the talks that we've had previously, because open hardware is an enormous area. It's significantly more complex in many ways than open source software, and those of you who will have been listening to previous talks will be thinking to yourselves, well, open source software is complicated enough. Surely, things can't get more complicated than that. So rather than sort of walk everyone through all of the aspects of open hardware, what I intend to come up with is just some of the areas that we're examining, that we're looking at, and raise a few questions. And so from that perspective, I'm quite happy for this to be an interactive session. So if people have questions as they go along, I'm quite happy for people to leap in. And Steve and I had a chat about this earlier as well, and I'm going to be handing over to him as we go through the talk as well, because there's some really interesting aspects that the Open Compute project is working on that I think he's going to be able to shed light on some of the more sort of practical issues that arise. So anyway, let me see if I can find some slides. So hopefully you'll be able to see the slides here. I'm assuming that if you can't see them, somebody's going to tell me, which is great. So in terms of a little bit of background, it might be helpful to know what my interest in open hardware is. So I've been advising on sort of open technologies for probably over 20 years now, and I've been advising on open hardware issues for over 10 years. And the first issue that I came across was an organization that wanted to produce an open source licensed car. And I'm still working with them, and that's a very, very interesting project. But open source hardware covers a sort of very wide range of things, and we'll sort of go into that a little bit. So the first question is, what is open hardware and what is open source hardware? So the terms are sort of broadly interchangeable. So the sort of things that this tends to cover can be anything really. I mean, a lot of people think about electronics and things like circuit boards when they're talking about open source hardware, and there's certainly a lot of activity in that area. And I'm involved with the drafting the CERN Open Hardware license, and that came out of a project called White Rabbit, which is very much around creating an electronics device, which is basically a circuit board. And then that naturally leads to some of the components that you would find on circuit boards, so such as silicon chips. And then you can also have, more solid devices, more things that you would regard as being hardware. So things like sort of cases that you might want to put your electronics in, and the sort of racks that you might want to put the cases in, and it can be things like furniture as well. That could also be described as open source hardware. It can be mechanical devices. I mentioned cars earlier, but it can be components like motors motors and engines, it could be suspension parts. I've also dealt with open source boats as well. And it can be things like 3D artistic work, so things like a sculpture. There's no reason why that couldn't be regarded as being open hardware. And also things that come out of 3D printers as well. And indeed, with the RepRap project, you could, the actual printer itself is something that is 3D printed. You can use a RepRap to print another RepRap, or at least large components of it. But the question is, does it have to be solid things? I mean, the answer to that is no, it doesn't. It could be fluids. And this is something that's quite common when you're looking at hydraulics, for example. You might want to include in an open hardware design the recipe that you use for your hydraulic fluid. So it doesn't even have to be something that's solid. It could be a liquid or a gas as well. Probably more interesting fluids are open cola, and there's a number of open beers that are around as well that have been released under open source licenses. So it's a pretty broad spectrum of things that can be regarded as being open hardware. So are there any definitions around this? What would you actually define as open hardware? Well, probably the best place to start is the Open Source Hardware Association. And they have a set of guidelines in terms of what is regarded as being open hardware. And not surprisingly, they have based this on both the four freedoms, which if you've been listening to any of the open source lectures, you'll be aware are derived from the Free Software Foundation, and also the 10 OSI criteria that make up the open source definition as well. They've sort of mashed them together. But you'll notice if you look at the definition that they are sort of very, very similar to those. So I'm not going to go through each of those criteria, but the best thing to do probably is to have a look at the intro to that, which is very closely modelled on the idea of the four freedoms. And it says that open source hardware is hardware whose design is made publicly available so that anyone can study, modify, distribute, make and sell the design or hardware based on that design. And then that immediately makes you start thinking about licenses and so on. So, okay, let's start with the question. Do we think that a chocolate cake can be open hardware? I mean, does that mean that the recipe is a design document in any way? So we're starting to get into quite an interesting question here about, although a recipe is something that clearly itself can be protected by copyright, is the cake itself something that's subject to intellectual property rights? And we'll look at that a little bit more in greater depth shortly. So one of the assumptions that people tend to make when they're mapping open source software onto open source hardware is that it's all to do with licenses. And it's a reasonable assumption to make in the world of software, because software is automatically protected by copyright as soon as you make it. So in order to open source it, you need a license. And you will always find that open sourcing involves some sort of license. I mean, there are one or two very minor exceptions to that, but 99.99% of the time, if something is being open sourced, that's because it was something that's protected by copyright and has then subsequently had an open source license attached to it. Is it possible to say the same about hardware? And it's quite interesting when you look at these assumptions, because, for example, the world of fashion is much better protected in some countries than in others. So the assumption is that this is something that has enabled a whole infrastructure of fast fashion to come into effect, because you get organizations that can very, very quickly replicate the design of something that appears on the catwalk, and suddenly that becomes a mass market product. And the question is that something that is protected by some form of design right? And in some jurisdictions it is, and in some jurisdictions it isn't. And it's generally regarded, for example, that Italy has very strict design rights around this sort of thing, whereas the UK is much more relaxed. So we have this distinction between things that are protectable by intellectual property and aren't protectable by intellectual property. Another example is database rights, for example, where in the EU and the UK there is database right. In the US there isn't. So you have a situation where you have one jurisdiction that has intellectual property rights in a particular area, another jurisdiction that doesn't. So if you have an open license, which opens up the intellectual property rights in the jurisdiction where they have them, and therefore makes whatever the item is equivalent to the same item in the other jurisdiction where there weren't any intellectual property rights in the first place, do they both qualify as open hardware, open data, open source software? And there shouldn't necessarily be a distinction between those, but it's just something that we need to bear in mind when we're talking about open hardware, is that there may be things out there that could be reasonably regarded as being open hardware, even though there aren't any underlying intellectual property rights in the first place. And there's a lot of IP challenges around open hardware. I mean, first of all, the range of intellectual property that tends to impinge on hardware tends to be a lot broader, and it impinges in different ways than the way that it necessarily impinges on software. So we have copyright and patent, obviously, and they're applicable to software as well. Then we have question of design rights. Then, it could be things like plant breeders' rights. The semiconductor topography rights, which are similar to artistic work copyright, but relate to silicon chips. There's also the question of database rights, which can also exist in open hardware as well, because it may be an important piece of the design documentation, for example, that you have a database of all of the electronic components that fit into a circuit board, so that could potentially be covered by database rights. So we have a very broad range of intellectual property that potentially covers open hardware, and it covers it in sort of much more extensive and subtle ways, and it varies depending on the type of hardware, etc., etc. And with software, you've got many chances for copyright to apply. And every time you have an opportunity for copyright to apply, you have an opportunity to introduce a license, and that license can impose various conditions like reciprocity and copyleft conditions. With hardware, that's not necessarily the case. So with copyright, you need to have a license when you're downloading software. It could be when you're installing it. It could be when you're running it, when you're distributing it. All of those circumstances involve the impingement of intellectual property in one way or another, and therefore you need a license to enable to do it. With hardware, that's not necessarily the case. You don't need to have a license every time you use a hammer. You don't need to have a license if you pass a hammer on to your friends and let them use it as well. So this is one of the issues that we have to think about is, first of all, what licenses are appropriate bearing in mind the different sorts of intellectual property that applies, but also what opportunities are there for the license to impinge on that particular activity in the first place. So that's another question as well. And what sort of licenses apply to open hardware? Well, with open source software, virtually all of the open source software will be subject to an open source software license. That seems fairly obvious. I mean, one or two people try to release software under Creative Commons licenses, which is regarded as not being a particularly wise thing to do, but it's relatively unusual. So most of the time when you're talking about open source software, you're talking about software that has been released under a specific open source license. With hardware, it's a lot more messy than that. A lot of people have released hardware under software licenses. BSD, MIT, Apache, and GPL are pretty common in the world of open source hardware. They've also tried to apply content licenses, such as Creative Commons licenses, which are fairly appropriate as far as the documentation is concerned. So, there's a degree of logic behind that as well. And then there's a number of licenses that have been drafted that are specific to hardware as well. So there's the suite of CERN open hardware licenses. And there's the solder pad license, there's the Tapper license, and from the Open Compute project, there are the permissive and the reciprocal copyleft varieties of that license as well. So that then leads on to the question is, how do we measure openness in the world of open source hardware? Now, fundamentally, software is made of ones and zeros, and there's an infinite quantity of ones and zeros, and you can, conjure them up out of nowhere. And when you're making software, the binary of the software from the design, the source code, then essentially you've got everything that you need to be able to create the final article, the binary piece of executable code, out of its raw materials, which is this infinite bucket that you've got full of ones and another infinite bucket that you've got full of zeros. And that's nice and straightforward. And it also has the advantage that zeros and ones cost absolutely nothing. They're completely free. Hardware is a bit more problematic because it's made of atoms, and atoms. There's plenty of different varieties of them. They messily combine into loads and loads of different sorts of molecules, which combine into lots of different sorts of mixtures. They have different costs of obtaining them. Even the same element can be extremely different in different forms. I mean, lump of coal is made of carbon, so it's a diamond, but making a diamond is something that is significantly more difficult than grabbing hold of a piece of coal. So you've got a lot more messiness involved there. And this then leads on to aspects of the sort of economic analysis of how open hardware operates, the development cycle, and so on. So one issue is with components. We've touched on the relationship of the design files, the source code for software, with the object code. So you take the source code and you compile it, and you end up with this executable which is full of ones and zeros, and you've got everything that you need there. That's it. That's as basic as it gets. Nothing in software gets any more basic than ones and zeros. So this assumption is that if you're provided with a piece of open source software in source code, then you have the ability to be able to get all of the way to the object code, which is the ones and zeros. But that is not necessarily true with hardware. Most hardware is made of components. You don't necessarily expect to have all of the instructions that you need to make every single component. You don't expect to have all of the instructions right down to atomic level to make something out of atoms. If you've got a circuit board, then naturally you would expect that the design to include the fact that you need to have components like resistors and capacitors, and transistors and so on, but you don't expect then to get the instructions on how to make those resistors and capacitors, etc. So if you don't have all of those instructions, does that mean that the design is truly open? For true openness, do you need to have the instructions to make absolutely everything out of a pile of atoms? And it seems like a silly question, but some of the definitions for open source hardware, it's something that they don't really take into account, because they assume that you can very easily map what happens in the world of software onto what happens in the world of hardware, and that's not necessarily the case. So that's sort of one issue around openness. The other thing that we sort of find ourselves asking in terms of whether something is truly open or not is, similarly with open source software, if there's a field of use restriction, does that cause a problem? With open source software, it's clear that if you have a non-commercial restriction, then it's not truly open source, because you always need to be able to take open source code and to use it in a commercial context. Is the same true of hardware? Yes, it probably is, but it's not quite as clear as it is in software. And similarly, in terms of IP restrictions, so in terms of patents, for example, if you have the design of something which is available under what you regard being an open license, and that gives all the rights that you need to be able to make the design. You recall, if we go back to the original definition, that you also need to be able to modify the design, and then to make articles to the modified design, and then to be able to pass those articles on to somebody else. So there's questions around, okay, you may be able to do that with the copyright licensing regime that you've got, but does the patent licensing regime extend that far as well? And this is an area that is subject to a sort of spectrum at the moment within the world of open hardware. It's nothing like as clear as that in the world of open source hardware, where the extent to which you need to be able to have patent rights to be able to both modify the hardware and to be able to create modified hardware for the underlying designs. And Steve, I was wondering if you might want to sort of step in here and talk a little bit about the Open Compute project licenses, because they have some quite interesting provisions in them as far as the patent licensing is concerned.
Yeah, well, there's a couple different ways, as Andrew mentioned, that you can license the product, but we do not take IP within the Open Compute project. We operate everything on a patent non-assert license. And there's a couple different ways you can do the permissive or the restrictive, and everyone signs a contribution license up front. And then even within Open Compute, you can work inside a particular project under a joint development agreement, and that allows organizations to work on a particular project and then share the results with the broader community. Prior to joining that particular project, you must agree that everything you work on will be made public. And so there's some really finite areas around GPU accelerators that require those type of agreements. But Andrew, you would probably be better to articulate your view on whether or not Open Compute licenses and how they relate to other areas of hardware and the positives around that.
Yeah, brilliant. Thank you. Yeah. So that leads me on to the next bit very nicely, actually, because I think with software, there's a general assumption that you can largely claim that any software which is released in source code, and if it's released under an OSI or Free Software Foundation approved license, is going to be open source or free software, as the case may be. So it's very much around the question of, once you have the source code and you've got that source code with a license that you know is compliant with one of those definitions, and pretty much all licenses that are compliant with one definition are going to be compliant with the other one as well, then you've got a piece of open source software or free software, which again is pretty much the same thing. So that's nice and straightforward. You really don't have to apply any other criteria to that. With hardware, it's significantly more complicated than that. I mean, the Open Source Hardware Association definition does go somewhat further. So in order for something to be regarded as being compliant with the Open Source Hardware definition, interestingly enough, it has to be made public. And there's no requirement for, under either the Free Software Foundation for Freedoms or of the OSI open source definition, that the software is made public. I mean, the reality is that it's a sort of bit of a moot point, because as soon as anyone gets hold of software which is licensed under a compliant license, then they are immediately able to make it public if they want to. So the reality is that anything that has been released is very likely to become public very quickly. So this is probably the reason why this is an assumption that has never actually been questioned. But it's just, so it's more of an interesting lawyer's point than anything else. There's also a requirement under the open source hardware definition that if the hardware contains interfaces from software, because quite a lot of hardware, especially things like circuit boards, electronic devices, will include some software as well in terms of firmware, for example, that either that firmware itself has to be provided under an OSI approved license, which is fair enough, or if it isn't, then there are requirements around the interfaces being made available. So that's something that's a little bit more subtle. That's not a requirement of software in the same way it is for hardware. And what is probably more interesting is that the Open Source Hardware Association runs a certification scheme, and if you want to submit your hardware to that scheme, not only do you have to demonstrate that you've provided appropriate documentation and it's provided under an appropriate license, which is all fine and makes sense, but you also have to demonstrate that you have used open components where possible. So this is the first time that we have a sort of major divergence between where you are with software and hardware, because with software, as I said, you're always getting down to the ones and zeros. The assumption is that you can get right down to the atoms that you use for making software. With hardware, that's not necessarily the case. So you've got to be able to use open components where possible, and essentially that means either components that you have the design for, or components that are very easily and readily available. They're basically generic components, like a resistor, for example, 220 ohm, 3 watt resistor. Something that you can get hold of very, very easily. And this is why we've found that it's really not so easy to apply this definition of openness to hardware as it is to software, because with software essentially you're looking at source code plus license. Based on that information alone, you can determine whether something is genuinely open or not. With hardware, it's not quite as simple as that, because you really need to delve into the hardware itself a little bit more to discover how it's made, what the components are, etc., to come up with something that's a bit more meaningful. And this is relevant to the study that I'm working on at the moment with the European Commission. And what we're doing is we're looking at the impact and competitiveness of open source software and hardware throughout the European Union. And there hasn't really been a study previously that has examined open hardware particularly. And I think it's important to look at the whole spectrum of hardware, whether it's based on openness but is subsequently closed, because that obviously has an economic impact, all the way through to hardware which is regarded as completely open in every meaning of the word. And one of the ways that we made it possible to do this, because when we started the study to begin with, we did have a number of people who were slightly concerned about the inclusion of various projects, because they were saying it's not truly open, you can't study this, what you're doing is you're adding the imprimatur of openness to something that isn't. But obviously, if you're trying to look at the study, look at the impact of competitiveness of open source software and hardware, you need to look at things that are similar to open source software and hardware as well, even if they don't meet a strict definition, so you can make some sort of meaningful comparison. So to do that, we introduced a taxonomy of placing objects on an openness spectrum. And I won't go into that in any detail now. So anyway, finally get around to answering Steve's question. In terms of where the OCP licensing project, the OCP licensing model sits, that is very, very much towards the open end, but I don't think it goes all the way, because there are some quite rigid patent requirements in there. And in the context of what the project does, I think that makes a lot of sense, because the idea is that it's important to make sure that you're making a whole bunch of hardware which is compatible with other pieces of hardware and therefore must comply with a particular standard. And so I would regard it as being quite akin to a very open standards license. And you'll understand that a bit more when Steve gives you a bit more background information in terms of what the OCP is all about and what it does. I don't know if you want to sort of leap in now and say anything, Steve.
No, I think you summed it up very, very well.
Yeah, thank you.
Can I just ask a question?
Yes, of course.
Andrew, cheers. You've talked about the openness of the code versus openness of hardware,
yeah.
And the taxonomy. Do you also include in that the consideration of the openness of the governance model around that? Because I know there are certain open source projects where the code itself is open, but the governance model around it is more or less controlled. So in some ways, it's kind of not as open as you would think.
We do, and that's a really good question. So actually, we looked at 3 separate taxonomies for establishing openness. And the problem with that is, that there are some really good ones out there that are complicated, and they require looking at something like 10 different criteria to determine the openness of a project. And much as I would like to use those when we're asking people questions, we can't really focus too much on that. There's a somewhat simpler model that Simon Phipps has come up with, which is great actually. But again, I think on balance, that is probably still a little bit too complex in the context of the study as a whole. So what we're going for a much simpler taxonomy on to look at the openness of governance, and to do that, we're looking at a sort of number of criteria. So things like, for example, is the decision-making process transparent? Can everyone see what's going on? Does everyone have an equal opportunity to be involved? Obviously, subject to meeting certain criteria. I mean, there's certain meritocratic criteria, for example. So the simple answer to your question is yes, we have taken that into account. I'm not going to cover that anymore in this, but it is something that we're looking at, certainly. So
Fantastic.
Thank you for that. Right. So, I mean, one question that I'm going to leave this open because I don't really have an opportunity to talk about it in depth at the moment, although I do have a sort of 2-hour lecture on this if anyone's interested, is can copyleft and reciprocity work in open hardware? And the answer is I think it can, but there are problems with it. I think there is less opportunity for the intellectual property rights to impinge. You'll notice earlier when I was talking about software, I mentioned that there are many opportunities for a copyright license to be required whenever you're loading, running, installing, etc. software. And when you do any of those things, you need a license. And if you need a license, you've got an opportunity to introduce conditions, which is the opportunity that you have to introduce this idea of copyleft or reciprocity. So it's much more difficult to do that with hardware. There's also the boundary problem that we've touched on already in terms of components, and the question is that if you've got a piece of open source hardware which tries to impose some form of copyleft reciprocity, then as soon as you bolt that component onto something else, does it mean that there's something else you also have to have the availability of all of that designs for those as well to be released under the same license? And looking at it in the other direction, does it also mean that any components that it contains, you have to have the full design documentation for that as well? So that's an issue, something that we think we've dealt with quite neatly in the copyleft reciprocal versions of the CERN Open Hardware license, but again, I'm not going to go into the mechanism on that now. And then there's also some economic issues around the fact that it's probably easier to reverse engineer and replicate a hardware device, if it's certainly the mechanical end of hardware, than it is for software, and therefore essentially circumvent the licensing model by doing that, by essentially doing a sort of clean room reconstruction of whatever it happens to be. But anyway, there's a link here to an article that I've written on that if you're interested in pursuing that particular issue any further. So the way that hardware is developed is also quite different from the way that that software is developed, and it depends very much on the type of hardware that you're talking about. So if we look at a sort of simple cycle, hopefully you can see my pointer here, you always start with a design phase. And then what typically happens is that you will build something and then you will test it, and then you get this cycle going around of design, build, test, design, build, test, design, build, test. And then at some point, you'll decide that you're going to turn whatever it is that you've got into a product. So you'll productize it, and then that'll be made available to the customer. And so for software, what you're doing here is you're designing the software and writing the source code. You're building it by compiling it. You're testing it to see if it works. If there are problems, then you go back to the design phase and fix the bugs in the source code, build it again, and you go round and round this circle here until at some point you decide you're going to ship it. And how you're going to ship it depends on what sort of software it is. So if it's firmware, you'll build it into your device and send the device off. If it's a piece of software that you can download from the internet, you'll maybe just put it in an installer file and let people install it. It could be something that you're using on a SaaS basis, you're developing internally. So in that case, the end user actually never gets access to the source, the code itself anyway. All it's doing is it's getting access. All the customer is doing is getting access to the functionality of that software. But in most cases, as far as software is concerned, the productization process is pretty straightforward. With hardware, that can be a lot more complicated. You can design something in some technology that looks very like the same sort of technology that you would use to design or write software, and then you've got things like CAD tools where you can develop 3D models of things, and maybe you can build something quite easily as well. It may be something that's 3D printed design, so you just pop it into your 3D printer, or it could be a circuit board design, which if you don't want to make the circuit board yourself, you can send it off to any number of organizations that will create that circuit board for you, and then they will ship it to you at very low cost very quickly. And then you go through the same process of testing it, and if there are problems, you change the design and you go round this cycle. So you can immediately see that for some sorts of hardware, this is still a very quick, very straightforward cycle. But for other sorts of hardware, if you're sort of trying to make a dumper truck, for example, then you might be able to do some of that stuff in a sort of CAD designer, and then you build it, which in itself is a highly complicated thing involving, a machine shop and lots of milling machines and metal presses and foundries and so on, and then you test it. So to try to short circuit that process, you're going to try and simulate as much of that as possible, and this is where this bit comes in. So you'll find that there will be software available that will enable you to simulate some components, but not others. And so it very much depends on the type of hardware, the extent to which you're able to simulate. Now, if you're able to simulate, you've still got a pretty rapid cycle going around here. And so that means that the whole development process can be a lot more straightforward. But it also means that since all of this is happening in the digital domain, what you're able to do is you're able to pass and easily transfer your designs onto other people, and those other people can run the same thing in their simulations and test, etc., etc., etc. So it's very much more like software, and you'll be sort of thinking in terms of having that software sitting in places like GitHub and GitLab, etc. And that dynamic, the ability to be able to pass this digital information around, is something that is very much relevant to the area of open source software, and it's applicable to some areas of open source hardware as well, but not necessarily to others. So this is where we and I'm sort of running a bit short of time, so I will come back to this later if anyone wants to discuss it any more. We've also introduced this in the study, the concept of hardwareness. So what we're doing is we're looking at each stage of that development cycle to see whether this question of hardwareness is where it stands on the question of hardwareness. So at one extreme, it's very like software. It means what you're doing exists very much in the digital domain, and you've got information that you can very easily share with other people. And then it may be something that you can also do the testing in the digital domain. So you may be able to simulate things quite effectively in the digital domain, and that's also quite like software. But there comes a point at which maybe if you productize it, you obviously can't productize a dump truck in software. You obviously have to make the object to do that, and that's very, very much on the hardware end of the scale. So in terms of the things that make open source software work so well, there may be barriers to being able to apply those things in open source hardware as well, and that depends very much on the type of hardware that you're talking about. And things that additionally apply to software, apply to hardware, are the fact that you may have to have complex and expensive physical tools to make the hardware. It's a physical item, so you're going to have to ship it places. You may need a large space in which to make it. If you're going to make a dump truck, you're going to need a big factory to do that. There may be environmental constraints as well. If you're making silicon chips, you need to have a very, very clean environment, a special clean room, positive air pressure, all of that sort of stuff as well. And you're also concerned about the cost and quality of the feedstock that you're using to make it. You want the quality of the steel you're using, the quality of the plastic you're using. When you're talking about software, your feedstock is zeros and ones, and any zero is identical to any other zero, any one is identical to any other one. So you have a whole bunch of different criteria that you start to look at when it comes to open source hardware, when you're trying to analyze where it fits into the production process, for example, and whether the things that have been effective in making open source software such a success will also be effective in terms of hardware are concerned. So we're introducing this scale to try to analyze that in different areas of open source hardware. And so for each one of those 4 stages, design, build, test, and productize, we're looking at the extent to which is something that's like software and something that's like hardware as well. And another factor to think about is the replication cost as well. If you want to replicate the Linux kernel, it's going to cost you nothing, because you can just literally just do a copy function in your computer and it will just copy it. You know, computers are basically designed to copy things. That's what they're very good at. So you've got a bunch of digital code, which is the Linux kernel, and you just copy it and you've now got 2 Linux kernels. That's very straightforward. Clearly, if you're going to replicate a car, then the cost to do that is many tens, hundreds of thousands of pounds. That's a very, very expensive thing to do, even if you've already got all of the tooling and equipment, etc. If you haven't got the tooling and equipment, then you're starting to look at the costing millions, hundreds of millions of pounds to do that. So already you have this huge difference between the economics involved in replicating software and replicating certain types of hardware as well. But then you do have things in the middle of that. So an FPGA, which is a type of silicon chip that's essentially programmable to do special functions, the cost to replicate that is around $1. You can acquire one of these things for around $1, and you can make it do exactly what you want it to do by feeding it with something called a bit stream, which is in many ways akin to a piece of computer software, but is subtly different in some ways. And you've replicated the FPGA, and that just costs you $1. So there's a whole bunch of assumptions around open source software that people can make that you can't equally make as far as hardware is concerned, or that vary very dramatically depending on where you are. So, summary. First of all, open source hardware is much less mature than open source software is. We're still learning an awful lot. We don't understand a lot of the dynamics around business models, development processes, etc., etc. So there are similarities, but there are very big differences. And things like openness, it's not so clear how you apply the concept of openness to hardware that it is to software. So that itself is another subtlety as well. The licensing situation is a lot more complex because there's many more intellectual property rights to think about. But on the upside, there are many fewer licenses that have been specially designed for open source hardware, and let's keep it that way. So it's dangerous to assume that what we know or believe works in open source software works in open source hardware. Sometimes it provides a useful benchmark or comparator, but it's dangerous to assume that you can always map one very accurately onto the other. And the most important thing is to bear in mind that the real world, the world of atoms, not surprisingly, has much more of an impact in terms of open source hardware than it does with open source software. But the bottom line is, we are learning a lot. There's an awful lot of study to be undertaken. So with that, thank you very, very much indeed for bearing with me. I'm now going to hand over to Steve, who can explain how some of this applies to the very interesting specific project that he's been working on. So Steve and the Open Compute project.
Great, thanks, Andrew.
I will try to unshare as well if I can figure out how to do that.
Let me know if
that seems to work.
Coming through.
Yeah, great.
Great. So Andrew touched on a lot of great points, specifically around the definition of openness and the development cycle of hardware. So I'll be focusing on everything inside a data center, and that includes a rack where servers are located, where network switch operators are located as well. This idea of disaggregation is something I want to. It kind of runs through everything that we do at Open Compute. In the past, things have been bundled, and now with the ever-increasing need for things to be more purpose-built, there's this growing desire for everything to be disaggregated. So software disaggregated from the hardware, and even the modularity or the hardware itself to become disaggregated into various components as end users need purpose-built hardware. So there's 2 terms, and for those of you that may or may not be familiar with this, I just want to clarify OEM versus an ODM. An ODM buys components from an ODM or from a manufacturer, and they assemble them, they brand them under their own name, and then they sell them to the mass market. Whereas an ODM, or a white box manufacturer, is the actual design house. They're the manufacturer. They can specialize if need. They do full product design services. And then lastly, on the support side, you'll get these OEMs with full managed support contracts, whereas the ODM or the white box manufacturer might be more product centric. So from these two models, if I'm an end customer, if I'm a bank or a telco, and I want to buy hardware, I have these two options in front of me. I can buy an OEM, or I can try to do a white box or an ODM model. When you take the ODM model and you add open source to it, that is the essence of the Open Compute project. In the traditional way that innovation came, and Andrew showed this in his development lifecycle, where you design, test, and build, very similar, the technology flows to these OEMs. They decide essentially what comes out in the next release, what will satisfy the most users for the least amount of cost, and we can get the highest margin. In the Open Compute model, you have end customers working with vendors and suppliers in a collaborative environment to develop specifications and product designs that then can be moved to the end users. Large customers or customers of any kind, they like the idea of a multi-sourcing strategy. So when you're somebody like AT&T and you sit down with a manufacturer and you manufacture a switch, the idea is AT&T doesn't want just one manufacturer for that switch. They want multiple manufacturers. So what's happening is you have customers that are demanding, if we work on something together, you're going to open source it. And that is the essence behind Open Compute. And this all started back in 2011. This is an announcement from 2010 when Facebook announced that they were going to build their own data centers. And at that time, they were growing quite rapidly and outpacing their infrastructure needs. When they started from scratch, they asked a lot of questions. What can we get rid of the system? Can we run things at a higher temperature? And do we really need centralized power supplies? So as they worked through all of these design requirements with the manufacturers, they took it one step further and they open sourced their designs to get this pace of engineering. So the Open Compute project started then with the help of Microsoft, Goldman Sachs, Rackspace, and Intel. They created this project. Google recently joined the Open Compute project as a board member just 2 months ago. So across the project, we have 150 companies, 6,000 engineers, and about 189 to 200 contributions that have come through the foundation. We're just similar to the Linux Foundation for hardware in that we run on projects. We completely volunteer basis. We have around 15 to 20 projects, including the sub-projects, working on everything in the data center, from server configurations to rack designs to even the security angle. There's a big initiative now under the security piece where once something is manufactured, how many people touch that piece of hardware along the ecosystem prior to it being deployed at a cloud operator or an end customer? Who owns that root of trust? So that is something that the entire community is working on within Open Compute. And Open Systems Firmware, for those of you that may not be familiar, when a server is booted up, it has a bit of software on there that's usually been quite proprietary from a couple vendors. So there's an effort underway within Open Compute to open source that firmware, and that helps on the design phase to speed innovation. There's 4 things that we dictate everything that we do at Open Compute: efficiency, scale, impact, and openness. So these are the 4 tenets of Open Compute, and I'll give you just 2 quick examples. Here are proprietary OEM servers, and as you can see on the front, it's a nice little plastic piece of bezel with the brand name on the logo or on the front. This is a form of gratuitous differentiation. There are hundreds of them out there, and for what purpose they need to be branded and their own specific design remains unknown. Here is an Open Compute server, stripped down, vanity-free, and I'll point your attention to these green touch points within the Open Compute server. These green touch points is one of the attributes of Open Compute where it needs to be a toolless design. So I can replace any part of this server without using a tool within minutes. Just an example of the efficiency that we drive within an open community. One other quick example. In the back of a traditional server, you have these about 8 40 millimeter fans to cool the server. In an open compute server, it's a bit higher, and we use two 80 millimeter fans. And there's something that takes place called the fan cube law, where I can half the speed of my fan, and I reduce the energy I need to spin that fan by 7/8. So I increase the size of the fan, I can reduce the amount of energy I need to spin that fan. Another innovation out of OCP. How this translates into actual physical workloads. On the bottom, you'll see the inlet temperatures going into the server, and on the bottom, you'll see OCP versus a traditional server. This is a study done out of SK Telecom in Korea. And what's important about this is as Europe dictates more efficiency standards at the IT level within the data center, these type of numbers become quite important. OCP adoption in Europe, here's just 4 quick examples. So the London Internet Exchange is running a disaggregated open source, open networking infrastructure. And they've been doing this now for 3 or 4 years. And there's a link to the presentation here, and I encourage you to go listen to what they're doing here. They're quite progressive in the way that they look at their network. ING Bank out of Poland and Telefonica replacing all of their central offices with disaggregated open source hardware. And OVH, you may know that name as well. They have a location here in the UK, but they're a very large European cloud provider doing some liquid-cooled OCP servers as well. So we're seeing a great deal of adoption of this type of designs because they like the openness, they like the flexibility, and they certainly like the CapEx and operation and OpEx that you get with using open source hardware. So before I get into this right here, I wanted to ask Andrew. Andrew, you've probably worked with a lot of these type of manufacturers. So what are some of the reasons or what makes somebody nervous about contributing an open hardware design?
I think there's quite a lot of drivers to that. I mean, one of them is a sort of natural conservatism, and particularly around anything to do with intellectual property. The idea that somehow, if we are involved in making any form of intellectual property, we want to keep it to ourselves. It's always better to keep it to ourselves, which is why, in terms of any sort of open technologies, I'm very keen on the idea, fundamental idea that open technologies exist, open source models, whether in hardware or software, exist to create a very low friction collaborative R&D mechanism. That's the way that I see things operate. And I always use the example of saying, lots of big companies, they will collaborate on R&D, but normally the way they do that is by having piles and piles of documentation. The lawyers will work out exactly what's incorporated, what isn't, what happens to joint inventions, etc., etc. Proper open source development methodologies, they just get rid of all of that and make it a lot more straightforward for organizations to collaborate with each other. So that's what I really like to see in a sort of successful open source collaboration environment, is just the ability for anyone to come along, use all of the designs in the way that they want, contribute to the designs in the way that they want, in a very low friction and straightforward way.
Yeah, it's interesting. The customers are really pulling the hardware providers sometimes begrudgingly toward this concept. The development cycle, the fear of being copied is something I hear quite a bit. But to our knowledge right now, it's more the customer having a feeling of a sense of an insurance policy. If I have one specification and multiple suppliers, as opposed to being kind of locked into a proprietary vendor. It seems to we're seeing more hardware vendors kind of open up to the idea of saying, well, I'm not going to lose business. There's a chance I gain more market share if I'm more open. So it's a long battle. We're not there yet, but we're making some headway.
Mm-hmm. Yeah.
So there is one local company I wanted to mention out of Manchester, and this is Vesper Technologies, and they've done a great job of pivoting their entire business model over to open hardware in general. They're putting together an OCP Experience Center, and that'll be in their office up in Manchester, and we'll be on the lookout for more announcements around that. But that'll be a chance for people to come in, actually see the differences between a proprietary server and an open hardware server, and even do some POCs out of Manchester if needed. And it's speaking of the actual data center facilities, with these new designs, many of the facilities around the world are not capable or not optimized to handle open hardware. There are some power differences in the power, the rack design. There are certain things that you don't need in a data center. So we've developed a set of criteria where an operator can run through, do a quick assessment, and determine, can I actually handle open hardware? And we're fortunate enough in the UK to have 2 of these data centers that have been through the program, one out of Harlow, which is KO Data, and the other one, Rackspace, out of Crawley. So these 2 facilities can certainly handle open hardware and are pushing this as a differentiator in the market. The last thing I'll mention is around circular economy, and I know that this is a term that has been used quite a bit here in Europe. It's something that we're focusing on a lot in the hardware space. There's a company called IT Renew that is taking a lot of the hardware that's coming out of the hyperscalers. If you can imagine that 6 to 10 companies in the world account for more than 30% of the actual hardware that's being used, there's a lot of that coming out every year. They refresh their hardware 3 years or less. They pull all of that hardware out of there. So this is something that we're working quite a bit on. 46 million servers will be end-of-life between 2019 and 2023. We're taking that, IT Renew is sanitizing that hardware and then reselling it on the secondary market to not say emerging markets, but actual cloud providers. OVH is a good example where they're using second user hardware to run cloud services at a fraction of the cost of new hardware. So we're big proponents of this, and we're also involved in the CED, Circular Economy for Data Center Industry initiative that's happening across the EU right now. So with that, more information here that you can take a look at later on how to connect and find out information on Open Compute, or drop me an email at steve@opencompute.org. But thank you very much for the opportunity, and I'll kick it back over to the team at OpenUK.
Thank you so much, Steve and Andrew. That was really interesting. Does anyone have any questions?
I would like to just
running out of time.
Yeah, I'd just like to say one last thing is we recently have partnered with OpenUK, and it's one of the things I'm most excited about being local is really working with the team at OpenUK to do a lot of fun and interesting things. And you're one of the more innovative organizations around the world, taking the time to really drive open hardware and software together. So all the countries have different organizations running on separate tracks, but you guys are doing the 2 together, which is great.
Thanks, Steve.
I have a question because I am aware that there was just recently work on open hardware license, I think connected with CERN, something with CERN. And Andrew, if I may ask, what is the biggest lesson learned for you within this process?
Oh, that's a really, really good question. I think it's try not to expect the license to do too much. And we had a lot of people who wanted our license to incorporate all sorts of really worthwhile things in abstract, like, for example, ethical issues, like sustainability, like repairability, and in abstract, each one of those things individually is very important. But there's only so much that you can ask a license to do. So I think we took the view at a fairly early stage that all we want to do as far as the license is concerned is to try to make the design as accessible as possible to as many people as possible, and also if you're choosing the reciprocal version, one of the reciprocal versions, to try to make the designs available to anyone further downstream who therefore adds the design, so in the same way that a reciprocal open source software license does. That's all we wanted it to do. So we're quite supportive of efforts by the Open Source Hardware Association, for example, to look at certification, that are looking at things like making sure that you can actually build the thing. And also other organizations that are looking at ethical issues and sustainability, environmental issues, and so on and so forth. That's all very important, but it's not the appropriate place to look at that in licensing. Licensing is not intended to do that job, and we don't want it to.
Great, thank you. Unfortunately, we've run out of time, but just to say again, thank you so much again for your time, and thank you so much for your really interesting presentation. Just to let everyone know, we've got 2 more sessions left in July before we have a break in August. So next week we have got Josh Didario talking about open innovation in the private and public sector. And then the week after that, we have Sarah Thomas talking about open knowledge is not neutral. So we'll then have a break in August and are back in September and kicking off with Amanda talking about commercial models in open source. So thanks again for your time, and hopefully see everyone next week.
Brilliant. Thanks for inviting us.
Fantastic.
Thanks for the
Thank you.
opportunity. Have a good
Thank
day.
you.
Thanks very much.
Cheers.
Bye.
Bye.